Namaskar. So in this lecture we will see about equipotential surfaces and some properties and how we can associate with the electric field. So let's see. So equipotential surfaces are defined as those surfaces for which each and every point have a constant and equal potential. For example, let's say you have this charge plus Q, okay, and all the surfaces which are having same potential, they will be called equipotential surface, right? So here we can understand in a simpler way. Let's say there is some origin O and you have some charge at point R, from this origin, right? So here the potential can be given as 1 upon 4 pi epsilon 0 Q by R. That's right. Okay. So it means you see that for a given charge, if R is fixed, the R is constant, then the potential will be constant. So all that concentric point here, right? That whatever for which you have same R, they would have equipotential potential would be same. It means they will be equipotential surface. So for example, you talk about concentric spherical surfaces, they will be having equipotential. So from here we also get a very important point here, that if you see that from point charge, that electric field is always, if it is positive charge, is readily outward or inward depending upon positive or negative. But interesting point to note here is that this electric field direction is perpendicular. If you take a tangent here, this is always perpendicular to the electric field, the equipotential surface. So it also brings a very nice property, like the electric field direction, the equipotential surfaces are those surfaces at which the electric field is perpendicular, right? Like here it is perpendicular. So for example, let's say you can have a uniform electric field, let's say something like this. Okay. Now you can have equipotential surfaces, which is perpendicular to the electric field, for example, like this, right? So these surfaces which are perpendicular to this electric field, they will be called equipotential surfaces. And you can say, you can prove it very easily, that why that equipotential surfaces, the electric field is perpendicular. For proving it, let's consider that it is not perpendicular, right? So if the electric field is not perpendicular at equipotential surfaces, it would mean that there will be there will be no net electric field, right? It means if you move a charge from this on this plane from one place to other place, if there is a net electric field, then work have to be done by external force, right? And if work is done, then that will be stored as potential energy. Then there will be changes in potential energy if it moves from one point to other point on that plane. If saying that it is equipotential, that just contradicts the point that it is equipotential, because the potential should not change on equipotential surfaces for the given charge if it is moving on that. So obviously that electric field would be perpendicular on such surfaces. So this is where the concept comes, where you get that equipotential surfaces, the electric field would be perpendicular on the plane. So for example, you have electric field in the direction of x, then the the y-axis on all the plane which is in the direction of yz plane, they will be having equipotential surfaces, because the electric field in the direction of x. So also based on this discussion that electric field is perpendicular to the equipotential surfaces, you can draw the equipotential surfaces for your dipole or multipoles, or for example if there's two similar charges. For example, let's say we take the example of dipole. Let's say you have this negative charge here and you have the positive charge here, right? So this is forming the dipole. So now the question is that if I have to draw equipotential surface for this, then how it should be drawn? What would be the status? So here again, as I said that electric field is perpendicular to the equipotential surfaces. So to draw the equipotential surface, you just have to find out the electric field lines, and then you get a perpendicular to that and keep joining those curves. You will get that the equipotential surface, based on the above discussion. So for example, for that we know that how you draw, as you have seen our first chapter, that how to draw the electric field lines. It starts from the positive charge inside the negative charge, right? And for dipole it would be something like this. Okay. And if you notice that here the field lines would be denser here, right? Because it means then the electric field will be higher here compared to the other places, right? And here it would be slightly sparse. So it means that electric field in this region is higher compared to this region. This is higher compared to this region. So it means that if you bring any charge from point type to this point, you have to do more work if you bring it here compared to this point, right? So it would mean that the potential would be higher and more denser in this case where you have to do less work to bring, right? So it means then if I have to draw the equipotential surface, so let's try it. So to draw it again, let me make it fresh image here. Okay, so it would mean that you draw a perpendicular, right? At each point you draw a perpendicular, then you will get something like this. Okay, and also saying that there should not be on the equipotential surface, there should not be any electric field gradient. If it is there, then of course that will not solve the problem. It should be uniform and it should be perpendicular to that point. So then it also brings into the picture concept of the electric field line density, because if it is denser, then electric field will be more there, and it means then you have to the potential would be, energy would be more. So for the same potential you should have a higher electric field to compensate that getting the equal amount of energy to bring that charge, right? So it means you can, in other terms, you can say that if you are bringing a charge from a point to that point, then all those points where the equal work have to be done, then they would be equipotential surface, right? So it means the force would be equi proportional to electric field. So it means that you may have a the curve, it may be shifted, it may not be concentric in this case, because the electric field is not same here in the case of dipoles, right? Here it is denser and here it can be relatively sparser. So if it is denser, then you may have a let's say some electric field if it is given by the field's length. So let's say with the equivalent to the length here, if we plot the electric field, then it would be farther in this case, right? Here it is a closure, so you may have the equipotential line something like this, right? Something like this. So it may be it will be shifting like this. So it may be not concentric, it may have a slight shift. So similar can apply to your this case. So it can have something like this. So for closure values it may be looking centered, but for larger it may be it's shifting towards like, so the center may be shifting slightly for the concentric circles if you draw, right? So it may be moving towards this for positive charges and towards this for negative charges. It means that center for that concentric circles, if you talk about, that would be shifting towards this direction for negative and this direction for positive once you move apart, because that electric field should be similar on those, and depending upon the field lines, electric field will be not same at the same concentrating point, because this is influenced by the nearby electric field lines, right? So now you understand the concept, like why in case of dipoles and negative positive, if you draw equipotential surfaces, you will see a shift in the center of the circle which you draw. It may not be exactly at the point, the charge cannot be exactly at the center of that. So that's the reason, like it also depends upon the electric field intensity, and of course at that point it should be perpendicular. So that's why you get the circle. the two isolated circles. The similar concept you can apply, and you can think of the same for the two positive charges. So the two positive charges, to draw equipotential surfaces, the same analogy you can think that the field line should be something like this. Okay, so it means that it would be something like this, the field lines. So if I have to draw the equipotential surfaces, so you can see that here electric field is almost compensated. So here you are not getting any matching curve, but here in these cases you can have something like this. Your surfaces would look something like this, right? And here it is sparser, so electric field you may have relatively lesser compared to the other region opposite of the previous one. You can draw the, sorry, I just cut it, it is not possible to cut, so let me redraw it. So this something like this. It is circle though, just the center is slightly shifted, or sometimes it may have some X-shape kind of thing. So similarly here, so you have a more load towards the lesser denser part, right? And at the farther away it can look something like this. Okay, this should not cut some anywhere, so let me clean that. Here remember this area, this should not be cutting anywhere. If it is cutting, then there is a problem, then you just missed the main concept. It should not cut anywhere. Okay, so this is a very rough diagram, no? You just make a, you can make it, but of course in a bare hand it is difficult to make. But here I wanted to show you the concept, right, that how you can draw the equipotential surfaces. It will be always perpendicular to the electric field line, and also depending upon the density it may shift towards one or the other, or the electric proportionality constant, because you have to bring the charge from infinite to that point. So the work done should depend upon the electric field. So if higher electric field, if you draw potential equipotential surfaces, then here electric field is higher and here it is lower. So if the sparser line means you have to go a little far compared to this point to get same work done, because here electric field can be lower because the field density is less, right? So this is about how you can draw electric field lines, equipotential surfaces for similar charges, a pair of similar charges or dipoles. Now moving further, and let's see some relation, how we can relate the between field and potential, relation between field and potential, relation between field and potential. So to find the relation between field potential, let's assume that we have a surface something like this, okay, and the other surface is for this one, let's say, this is the bottom one, so just make a shape, and let's say this is your surface A and this is your surface B, and this is some point P on the surface B, and the electric field direction is something like this, right? This is your electric field direction here, E, and let's assume that potential at A is VA, which is V, and here VB is V plus delta V. In the direction of electric field, let's assume that it is plus delta V, the higher increment in that, right? So if you bring a charge from point P to from plane B to A, you have to do some work, right? So that work would be how much? So potential difference would be equal to potential difference. So the work potential difference for B to A we talk about, right? So it would be we are bringing from charge from this plane to this plane, so the potential of VA minus VB is equal to V minus V plus delta V. Okay, and that should be equal to the work done. So let's say this is the electric field magnitude and the dl is the distance. So you are they are separate, the two planes are separated by a small infinite distance, let's say that is delta L, right? So this should be the work done. So if I have to write it, so I can write this the magnitude would be negative of, because V minus V will be cancelled, delta by delta L. This is infinitely small distance, let's say. Okay, so it means that the electric field, the value is negative of that potential. It would mean that what it means, it means that if it is coming negative, means in the direction of electric field the potential decreases. It means that the electric field direction is the direction in which the potential decreases steepest. So that's the one point you get from this observation. You can write it as modulus of V upon dl. If you want to replace it in the form of plus. And the other point you can make here is that the magnitude. So talking about this magnitude, it is the magnitude of the potential difference between the two planes, perpendicular to the displacement of the at that point. So, and the electric field magnitude is given by what? It is given by that magnitude of the potential difference per unit displacement. Normal to that, we are moving here normal, right? So normal to the equipotential surface and at that point, right? So this is the 2 points. One, as we mentioned, that the electric field decreases in the direction of potential decreases in the direction of electric field, and the second is that the magnitude is proportional to the potential difference per unit displacement in the direction of normal to the equipotential surface. So that 2 points is important in this case. So this is about equipotential surface and how to associate with the electric field, drawing the equipotential surface for two system of charges, for example 2 positive charges or 1 positive 1 negative charges, and how we can relate the field with the potential, this is a very nice property which we just saw, that how we can find out potential for electric field, or even the property of perpendicularness to the equipotential surfaces and field. So this is all about this lecture, and again we'll discuss next in our coming lecture, which would be potential energy for a system of charges. So see you there. Thank you.